This video is going to look at how we relate work to physical changes, or the changes in how an object is moving specifically. So if we're looking at the work energy theorem, if an object has work done on it, it must be acted on by a non-zero net force. And this just comes from remembering that work equals a force times a distance. So if I have a force acting on an object and it's moving, well then that force can do work on it. So Newton's first law says that if there is a non-zero net force on the object, it must accelerate. And in this case, we know specifically that it's going to be changing speed, because we know the force and the movement are kind of pointed in the same direction. We want to talk about, related to this, the kinetic energy. And the kinetic energy is the energy associated with motion, and a change in kinetic energy, so delta Ke, is equal to 1/2 m times the change in the velocity squared. So notice I have to square the velocity, square the final velocity, square the initial velocity, and subtract them. So this delta v squared is equal to v squared minus v initial squared. It's not equal to the flip way around. It's not equal to v minus v naught squared. So just take note of that. We have to square them first and then subtract them. Don't subtract and then square. So this says if an object speeds up, it gains energy because this v gets bigger, so it gains kinetic energy. If an object slows down, it loses kinetic energy. And so we just saw that if an object has work done on it, it has to speed up, or it has to change its speed, or it has to slow down, which means that kinetic energy also must change. So work changes speed. This means that kinetic energy changes. And this relationship is known as the work energy theorem. And in mathematical terms, we say that work equals change in Ke, which can also be written as work equals 1/2 m delta v squared. So if something has work done on it and it's changing its speed, we use the work energy theorem to relate those. So here's an example. A jet plane is preparing to take off from an airport. Assume the plane has a mass of 40,000 kilograms and takeoff speed of 80 meters per second. The engines provide a net force of 1 times 10 to the 6th newtons. That should be 10 to the 6th. In other words, 1,000,000 newtons. And we're going to assume that that's the net force, that all the other forces are negligible. How far does the plane travel between the point where it has a speed of 20 meters per second and takeoff? So let's draw a couple of things here. So the mass is equal to 40,000 kilograms. The initial speed is 20 meters per second. They say it goes until takeoff, which we know the takeoff speed is 80 meters per second. So that's going to be our final speed. We're looking for this change in distance here. And we know that the force on the plane is equal to 1 times 10 to the 6th newtons. So looking at this, I know I've got some masses, some speeds, some forces, and so I'm thinking, okay, forces and distances will give me work, which will be related to my kinetic energy. So work is equal to change in kinetic energy. Work is also equal to force parallel times the change in distance is equal to change in kinetic energy. I want to find this delta x. I know the force. I know they're parallel because this is pushing in the same direction that it's moving. So delta x will have to equal change in KE divided by force. Change in KE I know is 1/2 m times the change in v squared. So delta x is equal to m times v squared minus v initial squared divided by 2f, just doing some algebraic rearrangement. This in turn will equal 40,000 kilograms times 80 meters per second squared minus 20 meters per second squared divided by 2 times 1 times 10 to the 6th newtons. 80 squared will be 6,400. Yeah, 6,400. 20 squared will be 400. Is that right? Yes. But I'm going to grab a calculator just to double check because now I'm second guessing myself. 80 times 80, yeah, 6,480. No, that's 81. 6,400. Let me actually just throw all these numbers in together. So 6,400 minus 400. So it's 6,000 times 40,000. So in the numerator, we get 240 million. 240 times 10 to the 6th kilograms meters squared per second squared, because these meters per seconds are going to get squared and are multiplied by kilograms. And then I'm going to divide by 2 times 10 to the 6th. Now Newton is a kilogram meter per second squared. So notice that my seconds are going to cancel, my kilograms are going to cancel, one of my meters is going to cancel. So I'm left with just 1 meter in the numerator. And we end up with 120. 240 divided by 2 is 120. 10 to the 6th divided by 10 to the 6th, that cancels. 120 meters is my distance. So from the time that it's at 20 meters per second until it takes off, it travels 120 meters.